So we're going to look at a game theory problem here. Given a payoff matrix, we're going to try to figure out what the optimum strategies are for our players A and player B. If we look, this isn't a strictly determined game, so we have here we have the row minimums and the column maximums. So we don't have a saddle point, so this isn't a strictly determined game. So we're going to figure out what we can do to determine optimum strategies for each player. So first what we're going to do is, so we've got player A and probability that player A will choose row A or row B. You multiply this by our payoff matrix, we get a system which looks something like this. So the expected value when column 1 is chosen by player B would be 6 times P1 plus 0 times P2, or just 6P1. And then for the expected value for player B choosing column 2, we've got 2P1 plus 3P2. So what we're going to do with these equations now is set up a minimization problem. So we're going to say minimize W equals X plus Y such that 6X is greater than or equal to 1 and 2X plus 3Y is greater than or equal to 1. So we use the coefficients from these two expected values, 6 and 0, 2 and 3, to create our constraints. Okay, we'll have W equals X plus Y, and then we'll have greater than or equal to 1 over here. So for this, we're just going to solve this minimization problem graphically. So I've got, so using this equation, we've got 6x equals 1, or x equals 1/6. So we've got this line here, x equals 1/6. And then we'll have this line, 2x plus 3y, 2x plus 3y equals 1. So when x equals 0, y equals 1/3, and when y equals 0, x equals 1/2. So we have the points 0, 1/3, and the point 1/2, 0. This isn't drawn to scale, but we're going to have this line, and this will be, this feasible region. This is going to be our corner point right here. So if we can find where these two lines intersect, we'll figure out what the coordinates of this point are, x, y. So we've got x we know is 1/6, and if we plug that in to this equation over here, we have 2 times 1/6 plus 3y equals 1. This is 1/3. Subtract that on both sides, we get 3y equals 2/3. Divide by 3 on both sides, and we get y equals 2/9. Okay, so how we use this point here, xy, or 1/6, 2/9, we can plug that into our objective function. So w equals 1/6 plus 2/9. Finding common denominators, this would be 3/18 plus 4/18, which equals 7/18. So the value of this game is going to be the reciprocal of W, or 18/7. Okay, so that's the value of our game. Now, what can we do with that? So once we have this value, we can determine what the two probabilities will be. So P1 is going to be value times the x value here from our intersection. So that's going to be 18/7 times 1/6. And that's going to reduce to 3/7. So that's P1, and P2 will be value times the y-coordinate, or 18/7 times 2/9. And that equals 4/7. So for player A, the optimum strategy would be to choose row 1 3/7 of the time and row 2 4/7 of the time. And remembering, this is for a game played many times. Right, so there's the optimum strategy for player A. Now, to solve for player B, what we're going to do is we're going to take this, our minimization problem, and find its dual, or find a max problem to find player B strategies. So what we're going to do is so the coefficients of the objective function for the minimization problem will become the values, so this is 1x, 1y, so we have 1 and 1 here on the other side of the inequalities, which have been flipped, and then the coefficients in the maximization objective function will be these two values here on the other side of the inequalities, so 1, 1 here, and then if we consider the matrix 6, 0, 2, 3, in these constraints, the transpose of this, which is 6, 2, 0, 3, these will be the coefficients for these constraints. We have 6x plus 2y less than or equal to 1 and 3y less than or equal to 1. So there's our maximization problem. And again, we're going to solve this graphically now to find the optimum strategies for player B. So graph this, and we've got this line here, 3y equals 1. That's y equals 1/3. So we've got the line y equals 1/3. And then here we have a line when x is 0, y will equal 1/2, and when y is 0, that's actually an x. When y equals 0, x will equal 1/6. So we have the point 0, 1/2 right here, and the point 1/6, 0 over here. And there's that line, and we have a feasible region in here. So we've got corner points of 0, 1/3, 160, and then the intersection of these two lines. So the y value we can see is going to be 1/3. And plugging it up here, if y equals 1/3, we have 6x plus 2/3 equals 1. Subtract 2/3 on both sides, we get 6x equals 1/3. Divide by 6 on both sides, we get 1/18. So 1/18, 1/3 is the point where they intersect. So we've got corner points of 0, 1/3, corner point of 1/6, 0, and a corner point where the objective function equals 1/18 plus 1/3, or 1/18 plus 6/18, which is 7/18. So again, this is the maximum. And again, if we take the reciprocal, the value, as we found before, the value equals 18/7. And now to find the strategies for player B, Q1 is going to equal the value times the x value in our intersection. So 18/7 times 1/18, which gives us 1/7. And Q2 will equal the value times the y-coordinate, which is 6/7. So for player B, our optimum strategies are to play column 1 1/7 of the time, and to play column 2 6/7 of the time. That's sort of your quick and easy, fast and dirty. Fast and dirty, quick and easy, quick and dirty. Anyway, the simpler, hopefully simpler way to solve these problems using the graphical method.